Hello, everyone. Thanks for joining to the IoT webinar. We actually have some IT issues with my co-host. She has been struck basically with IT firewall issues when returning to the office. But no problem. I intended anyway to wait a couple minutes until all the attendees have joined. So please stay online, and I will start the webinar soon. So that's 3 minutes after the invite. So hello, everyone. Again, thanks for joining the Emnify IoT webinar. My name is Christian Henke. I'm head of product at Emnify. And today, I think we really have a great topic for everyone developing an IoT solution. It's how to select the best battery for cellular connectivity. And I'm actually super happy to have a great co-host with me. She might not be yet fully there. She's still struggling with the IT, but her name is Isabel. And Isabel, she has been working more than 10 years in the battery industry and will really share good knowledge, deep knowledge from her today. And that she has the knowledge, you will already recognize by her title. So Isabel is working as an application engineer at Saft, and Saft is a subsidiary of the Total Energy Group. Interestingly, for me as a German speaker, Saft actually means, translates to juice in German, so which makes perfectly sense for me because kind of the power, the batteries are the juice for your IoT project. So happy to have Isabel on board and really to share this knowledge here. Before I will hand over to Isabel, I want to give a little bit of background about the webinar series and why we are doing this. And just let me make sure this. So we have launched these Emnify IoT webinars now several months ago, and as Emnify, we know that IoT solutions have several different aspects to consider, and it's not only about cellular connectivity and its cloud integrations that we deliver. Yeah? So we therefore wanted to use this webinar series to do some knowledge sharing between our customers about the best practices and what they have used when developing their IoT solutions. So for example, last time we had Meter with us, Yannick and Max, who are one of our customers and are providing IoT solutions for the housing industry. And they talked about, for example, what antennas they used to master indoor connectivity issues. Further, we also want to get industry partners like Saft in to provide an overview of the state of art in their technology domain so that you have a good idea about what to choose or what to look for. When, for example, selecting your battery or your charger or maybe your IoT platform. So I hope you will enjoy this webinar series, and all sessions will be recorded and you will get the slides afterwards. As well, we always have a summary blog article with the slides and the recording, so you can do a recapture and share with your colleagues. Please comment if you like this series and what other topics you're interested in, so that we can plan accordingly. Just for housekeeping, after the webinar Isabel's presentation, she has done it, we will have some time to answer questions. So you can use the GoToWebinar question widget. So this should be on the right side of your screen, and you just type your question there during or after the talk, and then we make sure that Isabel has enough time to answer your questions. So let me just do a little check if Isabel is now able to connect. I see she unmuted.
I'm connected via Cecile's login.
As a team, very good. Managed the IT problems. Isabel, thanks again for joining. As already said to the audience, I'm super happy that you joined. I know you have deep knowledge. When we talked about let's say the content of the webinar, I was super surprised how much knowledge of how much considerations you have to take when choosing for an IoT battery, and looking forward that you share that knowledge with the audience.
I tried.
Okay, and then I will with that I will hand over to you. I will make you the presenter, and we come then back to the Q&A session where we'll ask some questions.
No problem. Is it okay?
Yes, now we can see your screen.
Okay. Sure. Yeah, I think I need to put it somewhere else. So, okay. Hello, everybody. So hello, everybody. I'm Isabelle Sormet, so application engineer at Saft Battery in Connected Energy Division. And my everyday job is to help prospects and customers to find the most adequate battery solution for their application. So today I will give you tips and advice I'm giving to my customers, mainly on how to select a battery for my cellular device. Why is the battery so crucial for our connected device? All connected devices need electricity, but most of them are not connected to the grid. Moreover, the accessibility to the connected device could be also difficult or costly. So the heart of every IoT system is power, of course. So at Saft, we're developing and manufacturing electrochemical systems for more than 100 years everywhere in the world. And the brand is well known for the performances and the quality of its battery used from the sea bottom up to space. So R&D everywhere in the world, the experience and clearly the batteries and electrochemical systems are the DNA of Saft. Saft is organized into 4 main divisions. From my side, I'm part of Connected Energy Division. And the aim of this division is all small devices where battery failure is not an option. If the battery fail in the field, the device is lost. So this is similar to the loss of the device. So many years of experience, many different chemistries in rechargeable, in primary, many different brands, and many different factories also. Saft is already part of many IoT applications, from small single nodes up to gateways. You can find examples of our main customers and applications in our website in IoT Market Selector. So smart city, smart parking, metering, smart industries, tracker, many different kind of application. So we will speak about batteries. A vast world, clearly extremely vast world. And the first question is, what is a battery? It's extremely complicated. Battery is chemistry that you're putting inside a tin can. Extremely complex. And when you connect a device, it generates electricity. The principle is always the same. You need a negative active material, which is the anode, the electron giver. You need a positive active material, which is the cathode, the electron taker. You need a separator to insulate the negative from the positive materials. You need an electrolyte, which is ion conductive, and you need a can. And when you have this, you have directly the negative and the positive terminal of the battery. And when you connect the device, the electrons are going outside the device from the anode through the cathode, and the ions are going inside the chemistry from the negative active material to the positive active material through the separator. And there are many different shapes of batteries. You can find single cells, cylindrical cells, prismatic cells, button or coin cells, pouch cells, many different kind. And you can find also battery packs, so with multiple cells. You can have cells connected in series to increase the voltage. You can have cells connected in parallel to increase the capacity. You can have multiple connection in series and in parallel to increase voltage and capacity in the battery pack. There is the outer battery shape, but internally also it depends. As example, for lithium thionyl chloride chemistry, so one of the most popular primary chemistry for electronic systems, you can find two different kind of internal construction, internal mechanical construction, bobbin construction or spiral construction. For bobbin construction, this is much more for high energy applications, so extremely long life duration with very smooth level of current asked. So for this kind of application, you have the lithium metal, which is in direct contact with the can. You have a separator. In the middle, you have a carbon catalyst. You have a nail in the middle. You fill with electrolyte. You close the cell, and you have directly the negative and the positive terminal of the battery. For the spiral construction, so it's for more higher power cell, so more higher level of current and a little bit lower, shorter life duration. You have one electrode in lithium, one separator, one electrode in carbon, and you roll it as a spiral, like a jelly roll, and you will insert the jelly roll inside a can before filling with electrolyte and close the cell. In terms of basics in electrochemistry, in an electrochemical generator, the voltage, the current, and the load of the application drive the chemical reaction inside the can. The energy produced is electricity, of course. The electrochemical reaction is between an oxidizer, the electron taker, the cathode, and a reducing agent, the electron giver, the anode. So the positive and the negative active materials. The electrons are used outside the generator through the device. So if there is no device, there is no current. If you have a look at the periodic table of elements, the nominal voltage will depend, or the level of voltage, the level of the energy density will depend on the chemistry of the anode and the cathode. So there are many different kind of nominal voltage for the cell depending on this electrochemical couple. More strong will be the reducing agent and the oxidizer agent. More high will be the energy density. So a high nominal voltage, if you have a look on lithium chemistry, it's on the top left, and and the oxygen, sulfur, and chlorus for lithium SOCl2, lithium thionyl chloride. This is one of the strongest electrochemical couple existing. And this is the highest nominal voltage you can find on the market. So it's more interesting most of the time for electronics application. Since the Volta battery in 1801, so more than 200 years ago, and there are many different kind of chemistries which has been developed for batteries. Lithium systems starting in the 70s and are today the most popular ones for all electronics powering. The red one in this slide are the chemistry used by Saft Connected Energy Division. And lithium manganese dioxide MnO2 or lithium thionyl chloride SOCl2 are the more dedicated specifically for IoT applications. So the advantage of lithium is the high energy density, low level of self-discharge, a stable voltage during the discharge. So it's a good match for IoT needs and long life and standalone solutions. When we are speaking about batteries, most of people think that rechargeable means longer life duration than primary. As an example, alkaline cells versus car lead-acid batteries. This is totally wrong. The most adequate solution for an application depends more on the specific use case of each application, such as for IoT device, the connectivity solutions. So for rechargeable cells, you will have a look on the cycle life. It will be more application for medium to high discharge rate, so amps. And generally on a temperature range from -20 up to 60. If you go on non-rechargeable cells, so primary cells, after it depends. You will have lower level of current, but you will have a lower level of self-discharge and a wider range of temperature. If we have a look on connectivity solutions, in the IoT world, the main questions are: how much data do I need to transmit? From where to where? How this data transmission does impact my energy consumption? I want to watch TV on my smartphone or only receive weather information from everywhere in the world. This is not the same kind of application. Industrial B2B applications are focused today on LPWAN solutions. So clearly LTE-M, NB-IoT, LTE-M Kate1 or NB-IoT, LoRa or Sigfox. As example, typical consumption of main LP1 connectivity solution with one transmission per day. If we have a look roughly for LoRaWAN application, the device will consume roughly 130 milliampere hour per year if there is one communication per day. For NB-IoT or LTE-M, it will be roughly 250 to 300 milliampere hour per year consumption. If I have a look on the traditional cellular connectivity, 2G, 3G, here it will be bigger than, the consumption will be higher than 4 ampere hour per year. So clearly, the traditional cellular connectivity is more compatible with lithium-ion technologies, which will be more designed for high current rate and with periodic recharge than for primary cell with a standalone systems. If we would like to give the first approach in cell size solution, for a 10 years life duration in the field, for LoRaWAN, it could be a AA or A size cell, A, C, or D size cell for NB-IoT and LTE-M. When we are talking about 2G, 3G communication, here it's more a complex battery pack solution with multi-D size cells connected in series and parallel. So clearly, if we are talking about primary in rechargeable, one cell could do the job. Now that I have my connectivity solution selected, what information can I find in battery datasheets to guide my choice? In battery datasheets, you will find, first thing, the nominal voltage, the operating temperature range. Sometimes you can find nominal capacity, but sometimes you don't have. You will find maximum continuous current, maximum pulse capability. How to properly use this information? The first thing to have a look is the voltage selection. If I take one example, so it's a AA size cell in lithium thionyl chloride, for example, I will find in the datasheet the open circuit voltage at 1 temperature. I will find the nominal voltage under a certain level of discharge rate at 1 temperature. And I can find also a curve, different curves, of the cell voltage versus the discharge rate for different temperature. Typically, when you have a look on such information, batteries are not constant voltage generators. Voltage means potential differences and depends on the current level delivered to the load, to the application. So if I want to check for one application, if I've got a minimum operating voltage of my electronics at 2.5 volts, I want to deploy my device in Europe in winter, outside in Europe in winter, it can go down to -20 Celsius degree. And my data transmission maximum peak current is 100 milliamp. If I have a look on the graphic in my datasheet, I will see quite quickly that over 2.5 volt for 100 milliamp, I don't have any data in the graphic. So I will need to test it. Typically, when I will do the test, on fresh cells, I will see different kind of voltage. Every time you, for lithium thionyl chloride, so SOCl2 electrochemistry, every time you ask for a current pulse, current peak, the voltage response of the battery will first drop down and after will recover. So you can have 3 levels of different voltages. You will have the open circuit voltage. You will have the minimum voltage reached at the beginning of the pulse, which is called the transient minimum voltage. And you will have the voltage recovery. So when the chemistry is more stabilized, and this voltage recovery is more close to the level of voltage you will find in the graph from the datasheet. On fresh cell, on such size of cell, you can have a quite nice voltage level. So there is no problem. If you test it only at 20 Celsius degree on fresh cell, you will say, oh, it will work perfectly for my device. But if I check exactly the same test on artificially aged cells, so here in this example, this is 1 month storage at 70 Celsius degree, I will see that even after 3 months, 4 months, I'm already at 2.5 volt. And 1 month storage at 70 Celsius degree, this is not 10 years life duration in the field. So clearly, I can say that perhaps it will not be the good solution for my application. So even when aged cell overlapping might be necessary, also it will depend on the manufacturer. Typically, this kind of result, so this is what we have on Saft chemistry with a Saft recipe inside the tin can, but you can have as many behavior as you have lithium thionyl chloride manufacturer in the world. It means that, for example, in the worst case of the market, for exactly the same test results, on fresh cell, you will have wonderful behavior. But if you spend a little time at hot temperature, you kill the chemistry. So you kill the battery. It will not work anymore. So in this case, clearly, in between both behavior, you can have as many behavior as battery manufacturer. So extremely complex to define if it will work for a long time or not. When you have such kind of behavior, clearly for 100 milliamp current pulse, this is not the good size of cell, or it is not possible to use the cell alone. There are different options regarding this behavior. You can change the construction, the internal mechanical construction of the battery. You can switch to spiral construction cells. Spiral will be more powerful, but you will have a shorter life duration. You can add a booster to the cell. So supercap, EDLC, hybrid capacitor, DC-DC converter, whatever, the many different kind of possibilities. But for this, you will need to check the leakage current of the additional component you add, because it will reduce your life duration. You need to check the internal resistance of this additional booster and the temperature range. You can also select another electrochemical system, such as lithium manganese dioxide, for example, which is spiral construction, much more powerful. But in this case, you will need to check the minimum voltage of your application and the temperature. Lithium manganese dioxide, it's a little bit more difficult than thionyl chloride at extreme cold temperature. And also the nominal voltage of the chemistry is not 3.6 volts. This is 3 volt nominal voltage. You have also other possibilities to switch to more complex battery pack configuration with several cells in series or in parallel. The battery manufacturers can help you on such kind of possible solution. In Saft product range, different solutions match typical IoT applications. Operating, so you can find for a pulse application solution, we will have the LSH range, so lithium thionyl chloride in spiral construction. You can find M or LM range, which is lithium manganese dioxide chemistries. And you can find also LSP range, so which is an association of the lithium thionyl chloride chemistry in bobine construction with an hybrid capacitor. So such kind of application are able to deliver quite high current pulse, up to 2, 3, even a little bit more level of current. Clearly, what will the first driver of any application will be the operating and the cutoff voltage. This is the first drivers. But other factors have to be considered. The second one which has to be considered, this is the capacity. How you will select the capacity, the nominal capacity of the battery. In terms of capacity, also in the data sheets, you can find many different kind of information. The main one is, this is also a graphic, and this is the capacity versus current at various temperature. It means that for one continuous discharge rate, you will have one level of energy available for your device. If I take an example quite quickly, if my device will consume 2 ampere-hour with a maximum data transmission peak current up to 100 milliamp and a consumption in sleep mode or PSM mode lower than 10 microamp. At 100 milliamp, I can find data, but not for all temperature in terms of available energy. But if I go at extremely low current, there is no information in the data sheets. Just as an example, here the lowest data you can find in this datasheet is under a continuous discharge rate of 350 microamp. And the available energy for this level of current, continuous current, is 2.5 ampere-hour. If I discharge 2.5 ampere-hour under 10 microamp discharge rate and I take only 1% of self-discharge per year, it means that the discharge time of this application will be longer than 15 years. It is clearly not realistic to wait for the testing results before giving a datasheet to customers. So it's clearly at low discharge rate, it's not possible to wait for the test results to be able to launch a product in the market. This is mainly why you cannot find any information in datasheets under such level of current. To explain you a little bit how this discharge rate influence the useful capacity. So this kind of graphic you will have in every lithium thionyl chloride chemistry, and you will find it also for other lithium chemistries. When you have this graphic, so the maximum capacity available is the nominal capacity of the battery. And this level of capacity is available for an application for a range of continuous discharge. So here, the size of this cell is a half AA cell, and you can have a 1.2 ampere hour from 1 to 3 milliampere continuous discharge. If you go at extremely low discharge rate, you have what we call the anode limitation, which is due to the self-discharge. The phenomenon is exactly the same as the evaporation of a liquid, of the sea, of the water in the lake when it's hot outside. So you will more consume the energy of the battery by its own self-discharge, by evaporation, than by the current from the application. And on the opposite side, you have what we call the cathode limitation, which give more an idea of how the cell is powerful or not. And this phenomenon is more close to the foam of a glass of beer when you try to fill a glass of beer so quickly, then you have more foam than beer. So there is a range of rates where the efficiency of the system is the optimum one. This is generally not the level of current peak, and this is generally not the level of consumption in sleep mode. There is one other thing you need to have a huge careful. Every data from the datasheets, battery datasheets for lithium primary are given for a voltage cutoff of 2 volts. If you have a minimum voltage in your application at 3 volts, you will not be able to use the whole energy of the cell. So don't forget the minimum voltage of your application. This kind of graphics is extremely important when you want to compare one manufacturer to each other. Every time you will first have a look on what is the minimum discharge rate shown in the datasheet. You can check that if there is no discharge data lower than 1 milliamp discharge, continuous discharge current, normally it's quite strange. And after, you can have a look also on the shape when you go on the anode limitation. So at a lower discharge rate, if there is a huge decrease of the capacity, it's an information that the level of self-discharge for this chemistry is extremely important. On the opposite side, you can have a look also on the shape of the curve under high discharge rate. What is the higher level of current which is noticed in the graphic? Is it 100 milliamp? If I've got 100 milliamp, is it 100 milliamp only at 20 Celsius degree, or do I have data at lower or higher temperature? And also the shape of the curve will give you an indication to compare how powerful is the chemistry from one manufacturer to each other. And after, so here the second selection was on the capacity selection for the battery. The third point is the operating temperature selection. Where do you want to deploy your device? Is it inside? Is it outside? Is it in Dubai, Cape Town, or Helsinki, or Toronto? Or in the middle of the Siberia? It has a huge impact. Clearly, temperature has the strongest impact on performances. Low temperature slows down the chemical reaction inside the can, and it's increasing the internal resistance of the chemistry. And high temperature will boost the chemical reaction, so it will increase the self-discharge and generate passivation for liquid cathode systems, which is lithium tunnel chloride is. So both restored capacity and voltage response will be impacted by the temperature. Also at electronic level, temperature will have an impact on the consumption of all the electronic components. It will not consume the same quantity of energy if you are at room temperature at 40, 50 Celsius degree or at minus 20 Celsius degree. If you want to feel a little bit what could be the impact of the temperature on any electrochemical system, you just have to think about your own body. We are all electrochemical generator. We produce electricity all day long and all life long. So how your own body reacts when you are in summer on the beach with 35 Celsius degree outside, or in winter at minus 10 when you are skiing. Your own body doesn't react in the same way. The electrochemical systems and batteries are reacting and impacting in the same way by the external temperature. So when you want to use a non-rechargeable battery for an application, you need to check all the external parameters. Temperature, what is the equivalent average current? What is the pulse intensity, duration, frequency, period? What is the minimum operating voltage of my electronics? You need to have a look also of some internal parameters from the battery. What is the chemistry self-discharge? Is this chemistry can be affected by passivation phenomenon or not? What is the nominal voltage of the system? And every parameters, all of these parameters will be linked to some battery performances, restored capacity, voltage response. Will there is problem under pulse or not at end of life, at beginning of life, etc., etc. So selecting the right chemistry, size, and configuration is a key to achieve a good life duration and a good quality of a product. And beyond all this chemistry, electrochemistry, and how it reacts internally, there is also some points that you need to pay attention in directly at the beginning of the design. The first one is how to integrate the battery in the device. There is many different possibilities to connect a battery to a device. The most popular one are battery holder, weld the battery on a PCB, or have wires and connectors. Clearly, my recommendation is to avoid any kind of battery holder for industrial and reliable applications. Battery holder is a connecting system for consumer application with alkaline cells. If you apply it with lithium batteries, lithium cells, it will generate micro-corrosion at the contact. It can generate additional voltage drop due to the contact resistance between the battery and the system. So clearly, most of the case in industrial and reliable application for long life duration, you can avoid any kind of battery holder. And the one thing also very important is what are the applicable standards of the device, the final device. We are today all working in an IoT world. Every device are connected. They are communicated with every time. There is a standard applicable for all communication technologies. And this standard need to add protections at device level, and battery have to be tested under specific safety standards also to avoid any risk of failure modes. The applicable standards can impact the battery selection. For example, if you add protections at device level, fuse, resistance, whatever is it can generate additional voltage drop. It will consume more, so it can have an impact on the selection of the battery. So you need to really, during the development phase, have in mind what could be the applicable standard of my device, and does this standard impact my electronic device? For Saft cells and chemistries, they are all compliant to the main battery safety standards, which are, the first one is the transportation. There are the UL also safety standards, the IEC safety standards for primary chemistry, for rechargeable chemistry. There are also specific standards which are relative to explosive atmosphere usage. So you can check all of this for any kind of battery manufacturer. It has to be compliant or qualified. For Saft, all the cells are qualified according to those standards. One specific focus on transportation: lithium batteries are dangerous goods. Whatever you do, this is dangerous goods. You need to have in mind, during the development of the device, under which condition can I transport my device with the battery inside? Will I transport the battery inside the device, or will I need to transport the battery outside of the device? This is not the same regulation to transport the battery, and this is not the same constraints. The second question is, how can I manage battery spare parts? If you want a device with replaceable batteries, how will I replace the batteries, and how will I need to transport the batteries? It's a question you need to have in mind at the beginning. And also, how can I manage end-of-life batteries, disposal and recycling? There are worldwide rules, national regulation, and it has to be respected. If it's not respected, it can be extremely dangerous for everybody. So it was an overview of the main different subjects. So as 5 takeaways to really have in mind, non-rechargeable batteries may last longer than rechargeable. Clearly, it's clearly not for the same application. You have higher nominal voltage, and lithium primary solution match many IoT cases. When you don't have to, with primary chemistry, you don't have to manage charge, you don't have to add a battery management system. The safety management is much more easier. The choice of connectivity has a huge impact on battery solution. Traditional cellular connectivity may lead to complex battery solution. So this is clearly more designed for lithium-ion and rechargeable technologies than for primary technologies. Knowing accurately the device consumption is important. Max peak, average consumption, cutoff voltage. All will impact the battery efficiency and how much energy I can use from the battery. Knowing accurately the device's environment is a key. Temperature impacts the battery capacity and voltage response. Where I want to deploy my device. My device will be located inside, outside, in the Middle East, in Africa, in Scandinavia, in Russia, in Japan, where? And the last but not least, there is no one size fits all solution. So ask for a customized support. It's really an help for most of the time.
Isabel, great presentation. I especially like this last slide about the 5 key takeaways. I think it's somehow you need someone to help you on the batteries, but I hope not everyone on the, let's say, on the audience, they have an understanding at least what questions to ask, yeah, and what to look out for. And I think
Exactly.
you have given a really comprehensive overview. So I would let now the audience give some time to ask some questions, and let's say would start the round. So I understand with traditional cellular connectivity like GSM, 3G, LTE, you cannot use a single cell, and with low power WAN, we're getting there. But what is actually the impact of the application? Yeah, if you, I mean, we have only talked about, let's say, the cellular module that needs these the current and the voltage, makes it mandatory to use the lithium batteries. What is the application impact? What do you see in the field, like, for example, for smart meters? How much consumption is really from the application compared to the cellular module? Do you have some?
For this, we don't know exactly at Saft batteries. We don't know exactly because most of the time, most of our customers know extremely well their electronic designs, and they send us the whole consumption of the electronics designs. So most of the time, we know which kind of communication module is inside, but we don't know exactly what are the other functions. We don't know what are the other functions from all the other parts and all the other components.
Yeah.
So it's sometimes we know a little bit, and most of the time with metering markets, mainly with metering markets, most of the time the biggest proportion of the energy consumption is coming from the sleep mode. It's not coming from the communication. It's not coming from the communication module. It's more the energy of the battery is consumed only during the sleep mode. It's generally few microamp, but few microamp during 10 or 15 years, it represents a huge amount of energy.
Okay.
So if you want to optimize a life duration of a device, generally, it's interesting to optimize the consumption in sleep mode. After, the communication protocol will have a huge impact on the selection because of the level of current peak. It's not the overall consumption of the electronics, it's the communication peak, because most of the time this is the communication protocol which has the highest level of current and also the highest level of minimum voltage. And if you go lower than the minimum voltage, you lose the communication and you lose the data transmission. If you lose the data transmission from a meter for a metering utility operator, it can have a huge impact, financial impact.
Yeah, then it's basically useless if you have connected device that's not able to send data.
Exactly.
We have now quite a lot of questions. So let me start. There was one question about slide 17, where you said that LTE-M narrowband IoT have a battery consumption about 250 to 300 milliampere. But with which configuration? PSM, either X, etc.
It's clearly an average of what we can see in all the information we have for several years now in this market. After, this level of consumption is given roughly for one transmission per day. If you transmit information once a week or twice a day, it's not the same thing.
Yeah, I think the question is about with which configuration, PSM or ADX. And if I recall, on slide 17, it was a little bit small, but I think you had the different currents for PSM, for example, defined, right, for the power sleep mode.
Yeah, in this typical profile I can give you, because it's written on the slide 17. But je peux changer de slide, Cécile?
Can you
I try to find the back the good Thank you. Here. You still see my screen?
Yes.
Yeah. So here in this typical profile, so this is a NB-IoT typical profile from a well-known module manufacturer. measured by a partner, and the maximum peak was at 310 milliamp for this NB-IoT module. But it can go for LTE Cat-M modules. You can have peak current up to 500 milliamp, for example.
Yeah, and
even
I also
if
see
the average consumption of the transmission will be more close to 120, 130 milliamp. But you can have peak current.
Yeah. And I think this also states that under PSM you have a quite significant lower peak amp of 8 milliampere.
Yeah, 8 milliampere during 30 seconds. Clearly, this is not an optimized system.
Okay. I think this answers the question. Let me just, I made the question panel a bit small. Is the lithium SOCL2 battery the most environmentally unfriendly or friendly? Do you have some, let's say, guidance on that, which is...
This is exactly what is saying at the end of the presentation. There is no, I will, yeah. There is no one size fits all, clearly. For some application, this is lithium tunnel chloride, which will be the most adequate solution. For some other, it will be lithium manganese dioxide. For some other, this will be lithium tunnel chloride, but with a pulse helper, an hybrid cap or super cap or something like this. Clearly, there is no one size fits all solutions. So every time it will be a trade-off for the electronic designer to try to have the smoother consumption with the smoother pulse level, with the wider temperature range. But even for the same application, depending on the electronics of the device, the whole electronics, you can have several solutions which could match and be really the best one. Sometimes you have only one solution which is able to work, but sometimes, for example, if you can use a lithium tunnel chloride cell with a pulse helper, so with an hybrid cap, for example, it could work perfectly for Dubai or for Paris. But if you want to use it at minus 40 Celsius degree in Russia, the hybrid cap, it will not work correctly. So you will need to switch to another chemistry or another system.
No,
so even for the same application.
I think, Isabel, the question is more about the environment friendliness. So is it a green cell to use the lithium SOCL2, or what's the impact when they are produced or when they stay in the field? I mean, the thing that I like about this is exactly the first takeaway here. So actually you don't need to have more electronics with charging or anything. You have the one battery for an application that lasts forever. So you, let's say, save the production of more electronics to recharge. Is there
for
any...
example, yeah, and also if you have, it's for lithium primary batteries, most of the time when you are talking about the different chemistry, if it's lithium tunnel chloride or lithium manganese dioxide, I think in terms of environmental or ecological things, it's quite similar. After, what is important is to be able to use as many energy from the cell. From my point of view, it means if you install a 1 ampere hour battery in a device, the objective of the device is to use as many energy of it. It's not to put the cell in the garbage if you after using only 50% of the capacity.
Yeah.
But this depends clearly on the adequation between the application and the selected battery.
Of course. There's another question. I don't know if I understand it. What is the importance and impact of using a protected cell? Are they highly desirable? Are there cases where they are not necessary?
Most of the lithium cells, primary cells, they are designed to be safe, but after it clearly depends on the battery manufacturer. With Saft chemistry, we always we always have what we call the double insulation between every component in the cell, between the positive and the negative material. We always try to have a double insulation. If there is a loss of one insulation, you cannot you have difficulties to connect the plus and the minus. So do an external short circuit. With Saft cell also, we respect all the safety standard, battery safety standards at cell level and at battery pack level when we are different cells connected in series or in parallel. After, it depends on the battery manufacturer.
So basically the safety standards already, let's say, define that you need to use a protected cell. So there are no cases where you would recommend not using a protected cell.
Okay. Exactly. No, for the cells, it's this is the first one of the first slide of this presentation. A battery. This is a chemistry inside a tin can. So when you put energy inside a tin can, if you do something wrong with the tin can, you will have problem, clearly.
That's why you should not throw batteries in the normal garbage, I guess. Also.
Exactly. And whatever is the battery and whatever is the chemistry inside. If you put energy in a container, you need to be careful with what you do. This is energy inside. Yeah.
But after, yeah. Isabel, you have so many questions, and I'm just cautious about the time. But I want to, let's say, at least address the questions that are here. You spoke of transient minimum voltage. Is this like the battery waking up each time you draw current from it?
It's not exactly this. It could be like this, but it's not exactly this. Lithium thionyl chloride chemistry, this is what we call liquid cathode systems. It means that the positive active material when you are at the positive active material, this is not the carbon support. This is not the carbon support within, this is not an electrode. The positive active material, this is the electrolyte. The electrolyte has two functions in lithium thionyl chloride. This is the ions diffusion from the two terminals inside the chemistry, but this is also the positive active material. And the negative active material, this is the lithium metal. It means that the two active materials in the liquid cathode systems are already in contact permanently. So it creates this contact, create what we call the passivation layer. And it's a natural insulator. This is a natural separator between the two active material. And as it is an insulating material, every time you ask for current, you need to break this layer. So this is why you have this initial drop every time you ask for a current pulse. This is the break of this layer. And every time the current stopped, there is the chemical reaction between the two active material, which recreate this passivation layer. So this passivation layer is mandatory. You need to have it to have a lower level of self-discharge, to have not an internal short circuit permanently inside the chemistry. But you need to manage it for the whole life of the battery correctly, to be sure that it will not become too strong, and so you will be able to power the device for the whole life of the device.
Thanks, Isabel. There's another question. What is the best battery type for use at -30 degrees with 100 milliamps transmit and a minimum voltage of 3.3 volt?
At -30 with a minimum voltage of 3.3 volt, 100 milliamp, clearly it will not be a battery alone. It will not be one cell. It's not possible. So it could be perhaps some lithium-ion chemistries can do this alone, but it's not with primary chemistries. And with primary chemistries, the only solution is to have several cells in series. So 2S battery pack. You connect 2 cells in series, and here you will have a nominal voltage which could be more close to 6 volt or 7.2 volts, depending on the chemistry inside the pack. But in this case, you need to manage the maximum voltage of the battery at electronic level. So you need to find other ways. But 3.3 volt minimum voltage with only one cell, even at room temperature, it will not work for a long time.
Okay. Isabel, thanks a lot. I think we're 5 minutes over. And there was one question about, will this webinar be available for download? Of course. So everyone who's registered will get the slides and the recording afterwards. And we will also do a wrap-up blog, which, let's say, also shows the key takeaways. So you can share this also with your colleagues. Yeah, if there's anyone also any ideas for next webinar where you have another topic you want to hear about, you're welcome to this comment. And Isabel, thanks again. It was really a great webinar. I see a lot of people here really appreciated the content, and yeah, hope you found this useful, and we can speak again.
No problem.
Okay.
It was a pleasure for us also.
Very good. Thank you. Have a great day, and speak to you soon.
You too.
Bye-bye.
Goodbye.